Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Fazullah, and in this lecture we shall study about the residue of a complex function. We shall give the definition of residue and examples to explain it. Then we shall learn some simple techniques for computing the residue of different functions. First of all, let us revise the concept of Laurent series, with the help of which we shall define the residues. In my previous lectures, we have studied that the Laurent series of a function f of z is a series of this form which has two parts. The first one is called the analytic part, the second one is called the principal part. And now let us write the definition of residue. We say that if a function f of z is represented in the form of a Laurent series, then the coefficient of 1 over z minus z naught, the coefficient of 1 over z minus z naught, that is B1, is called the residue of the function f of z at the singular point z naught. It is denoted by B1 is equal to a residue at the point z is equal to z naught of the function f of z, or sometimes we denote this that the residue B1 is residue of the function f comma z naught. From the definition, it is clear that if we are given a function f of z, first of all we have to represent it into the Laurent series. And then just look at the coefficient of 1 over z minus z naught. So the coefficient of 1 over z minus z naught will be our residue. In an informal way, I can say that the residue is nothing but just a coefficient of 1 over z minus z naught. And now let us explain it by some examples. Let us take a function f of z is equal to e power, f of z is equal to e power 1 over 2z. And the question is, find the residue of this function. Then what we have to do? First of all, we have to represent this function into the Laurent series form. Let us do that. F of z is equal to 1 plus 1 over 2z plus 1 over 2 factorial into 2z square and plus up to so on. And you can see that this function has an essential singularity at the point z is equal to 0. And the residue of this function f at the point z is equal to 0 is the coefficient of 1 over z, which is, we can see, 1 over 2. So this is the required solution. Now let us see another example. Let me have a function f of z which is equal to 1 over z cube plus 2 over z square plus 4 over z minus 5 minus 3z. Find the residue of this function. This function is already in the Laurent series. So we can see that this function has singularity at z is equal to 0, at which is a pole. So the residue of the function f at the point z is equal to 0 is the coefficient of 1 over z, and the coefficient of 1 over z is 4. So this is the required solution. Now let us see another example. In this example, I have a function f of z is equal to sine z by z. And the question is, find the residue of this function. So again, I have to represent this function into the Laurent series. So sine z can be written as z minus z cube by 3 factorial plus z5 by 5 factorial minus up to so on. And now I have to multiply 1 over z inside. So if I multiply 1 over z inside, I will get that f of z is equal to 1 minus z square by 3 factorial and plus z power 4 divided by 5 factorial and minus up to so on. Now you can see that this function has singularity at z is equal to 0, which is the removable singularity. And the residue of this function will be the coefficient of 1 over z. And we can see that the coefficient of 1 over z is 0 here. There is no 1 over z. So we can say that the residue of this function f at z is equal to 0 is equal to 0. Now let us solve one more example. In this example, we have a function f of z which is equal to z square into sine of 1 over z. And we have to find the residue of this function. So again, we have to represent this function into the Laurent series. So I can write z square, and again I can use the series of sine z. So I will write that 1 over z minus 1 over z cube into 3 factorial plus 1 over z power 5 into 5 factorial and minus up to so on. Now I have to multiply this inside. So I will get z here. Here I will get 1 over 3 factorial into z, and here I will get 1 over 5 factorial into z power 3 and minus up to so on. So now you can see that this function has singularity at z is equal to 0, and the residue of this function at the point 0 is the coefficient of 1 over z, which is minus 1 over 3 factorial, which is equal to minus 1 over 6. And now we have to learn a very simple technique with the help of which we can find the residue of some complex function f of z without expanding or representing the function into the Laurent series. So let us see the statement of this theorem. If z naught is a pole of order n, a complex function f of z, then the residue of the function f at the point z naught is equal to 1 over n minus 1 factorial n minus 1 time differentiation of the function f of z multiplied with z minus z naught power n at the point z is equal to z naught. From this theorem you can see that if we are given a function f of z which has a pole of order n at the point z naught, then what we have to do? We have to multiply z minus z naught power n with the given function. So of course you will see that this term will be cancelled from f of z. And then we have to differentiate that n minus 1 time. And at the end, after the simplification, we have to put z is equal to z naught and we will get the residue of that function. Let us simplify a little more. If f of z has a simple pole means it is a pole of order 1. So if n is equal to 1, just put 1 here, here and here, and we can see that residue of f at z naught will be equal to, this is 0 factorial which is 1, and there is no n minus 1 is 0, so means there is no derivative, and z minus z naught power 1, so we can write that this is z minus z naught power 1 only, and the function f of z. And of course at the end we have to put z is equal to z naught in the answer. And now let us see if n is equal to 2. N is equal to 2 means if f of z has a pole of order 2 at the point z is equal to z naught, in that case residue of the function f at z naught can be written as, again just put 2 here, 2 minus 1 is 1 factorial which is again 1. If I put 2 here, 2 minus 1 is 1. So I will get d by dz, and this will become z minus z naught, and let us put 2 here, f of z, and at the end we have to put z is equal to z naught. Similarly, if I have a pole of order 3, in that case the residue of the function f at z naught is given by, just put 3 here, we can get 1 over 2 factorial, and if I put 3 here, I can get d square divided by dz square into z minus z naught power 3, just put n is equal to 3 here, and f of z, and at the end we have to put z is equal to z naught. And now let us explain this by some example. So let us find an example. F of z is equal to, I have to write an example. The example is that f of z is equal to 1 over z plus 1 into z minus 2 power square. 1 over z plus 1 into z minus 2 square. This is some given function. And the question is, we have to find all the residue of this function at the given poles. So you can see, first of all we have to find the poles. To find poles, first of all you have to put the denominator, which is z plus 1 into z minus 2 whole square is equal to 0. And from this you can get that z is equal to 1 is a pole of order 1, which is simple pole. And from this you can get that z is equal to 2 is a pole of order 2. So this is a pole of order 2. So now I have to find the residue as z is equal to 1, and then I have to find the residue at z is equal to 2. So let us start from z is equal to 1. To find the residue of the function f at the point 1, you can see if n is equal to 1, we have to use this formula. Now in this case, z1 is 1, so I can write that this is equal to z minus 1. If I take 1, okay, sorry, this is minus 1. Z plus 1 equal to 0 will give you z is equal to minus 1. So I can get z plus 1 and f of z, and the point is z is equal to minus 1. Now just we have to simplify this. If I simplify this, I will get that this is equal to z plus 1, and I have to put the value of f of z. The value of f of z is this one, so I can write that this is 1 over z plus 1 into z minus 2 whole square. And the point is z is equal to minus 1. Now this term will be cancelled with this one. And now we have to just put z is equal to minus 1 here, and we can get that this is equal to 1 over minus 1 minus 2 whole square, which is equal to 3 square is 9. So the residue of the function f at the point minus 1 is equal to 1 over 9. So this is the required answer. And now we have to find the residue at the other point. So the other point is z is equal to 2. To find, we can see that if n is equal to 2, we have to use this formula. So residue of the function f at the point 2 is equal to, we can write d by dz, and I have to write z minus 2 whole square, and into the function f of z at the point z is equal to 2. Now just put the value of f of z. So if I put the value, I will get d by dz of z minus 2 whole square into f of z. What is f of z? This is 1 over z plus 1 into z minus 2 square at the point z is equal to 2. So this will be cancelled with this one. So now I have 1 more z plus 1, but I have to find d by dz of this function. We have to differentiate this. So if I differentiate this, I will get that this is equal to minus 1 divided by z plus 1 whole square. And again, z is equal to 2 is the given point. So now we have to put z is equal to 2 in this function. If I put this, I will get minus 1 over 2 plus 1 square, and we can get that this is equal to 1 over minus 1 over 9. So the residue of the function f at the point 2 is minus 1 over 9, and this is the required answer. Now we have to solve one other question. In this question we have to find the residue of a function f of z, which is equal to z cube plus 2z. Z cube plus 2z divided by z minus iota cube. Z minus iota cube. This is the given question. And we have to find the residue of this function. So to find the residue, first of all we have to find the poles. For the poles, put the denominator equal to 0, and from this you will get that z is equal to iota is a pole of order 3. And now I have to find the residue. To find the residue of the function f at the point iota, and in this case n is equal to 3. So if n is equal to 3, I can use this formula. Just put n is equal to 3. You will get 1 over 2 factorial into d square over d z square and z minus iota cube into f of z. And the point is z is equal to iota. This is our pole. And now we have to simplify this. So we can get 1 over 2 iota is 1 over 2, and here d square over dz square into z minus iota cube. Put the value of f of z. The value is this one. So I can write z cube plus 2z and divided by z minus iota whole cube, and the point is z is equal to iota. So this will cancel with this one. But I have to differentiate this function 2 times. So let us, this is 1, and I take this function as g of z. G of z is z cube plus 2z. Now differentiate this. If I differentiate both sides, I will get 3z square plus 2. Now differentiate it again. D square over dz square of d is equal to 6z. Now let us put this value in 1, and we can get so 1 implies that residue of the function f at iota is equal to, this is 1 over 2, and d square over dz square of z cube plus 2z, this is 6z, and the point is z is equal to iota. Now we have to put this point inside. So if I put this point, I will get 1 over 2 into 6 iota. If I simplify these 2 terms, I will get 3 iota. So residue of the function f at the point iota is equal to 3 iota. In the next lecture, we shall study applications of the residues. So we shall study the residue theorem, with the help of which we will solve different integrals. So